let's talk about the equations of lines in R2 or two space or two-dimensional planes. So this is kind of what we're used to from grade 9 and grade 10, working in two dimensions. And I guess grade 11 as well. We don't really do much stuff with 3D. So what do we need to identify a line uniquely in two dimensions? In other words, what are the minimal pieces of information that you must give me in order to guarantee that I will graph the one and only line that you were thinking of? And if we're doing this live in class, you can answer in the chat. Or if you're just watching this video, you can kind of think to yourself, what are the different pieces of information that I need to identify a line? So just a couple notes here. Two space means you're working in two dimensions. Or, in other words, we're working in R2. And uniquely, that keyword uni, so one of a kind. So there's only one way of doing it. We're not going to mix it up with anything else. And let's describe the common ways that we do this and that we've learned about before. First of all is slope y-intercept form. So y equals mx plus b. So what do we need to know here? So, and as an example, y equals 2x plus 3. So we have our slope, and we have our y-intercept. And as long as I know either slope plus 1 point, or if I know 2 points on my line, I can define it, because I can use my 2 points in my slope formula to find slope. Then I can sub one of those points in to find my y-intercept. Or if I have the slope and 1 point, I can sub both of those into my slope-intercept form and solve for b. And you've done this since grade 9 at least, so that is hopefully familiar to you. We can use point slope form. So if I know a point, x1 comma y1, and the slope m, I can write that like this: y minus y1 equals m x minus x1. Or we can write things in standard form, which can kind of look two different ways. Either we have ax plus by plus c equals 0, or sometimes it looks like this: ax plus by equals c. And we can see that in our line right here, given in our example here, that I have my x and y plane, and I have my point here. So I have my y-intercept given right here. So that's my 3 value. And I can find my slope either by identifying another point and calculating the slope, or I can just use my slope triangle. So I can go over 1 and up how far? 2. So nice little 90-degree right angle triangle here. Easy to work with. Over 1, up 2. So slope is rise over run. Rise is 2, run is 1. So our slope is 2. And so we can easily find our equation right here: y equals slope of 2, x plus our y-intercept of 3. All right, that's not too hard. We've seen this before. All three of these forms are Cartesian forms. They can easily be graphed on the Cartesian plane, and everything's given in terms of coordinates. So just like we talked about before with different kinds of vectors, with our geometric vectors, we know things like length and direction, but here we are dealing with, we're defining everything in terms of x and y coordinates on the graph. And I think I need to adjust my screen here a little bit. It's getting cut off just a little bit. Don't want to miss out on any exciting notations here. All right, and just remember, when we're talking about Cartesian stuff, scalar, and the Cartesian plane is our xy plane. So the flat surface defined by our x-axis and our y-axis, so the whole flat surface of my sheet or my screen here. All right, let's keep going. But how can we think about lines in a vectorly way? We will learn 2 more ways to represent our line: the vector equation and the parametric equation. First, let's talk about, and there's also symmetric equations, but that's not part of our course material here, so we're not going to worry about that. Start with our first example. Let's talk about vector equations of a line in R2 or 2 space. So remember, just dealing with 2 dimensions like we're used to from our previous knowledge. We're going to start with a point on the line, and then add multiples of the direction vector. Direction vector. So our direction vector is going to kind of be like our slope. It says this is the direction that you need to head in, and the point tells us where we're going to start our graph and where we're going to move from there. So first of all, our direction vector is going to look something like this. So direction vector M, where the values are the run, so my x value, how far over did I go, and my rise, how far up did I go. And very similar. Think about our previous ideas about slope is rise over run. We can find those values by looking at the graph, finding our triangle or whatever. So let's actually do that right away. Take two known points on the graph. How far over and up do I need to go? Over 1 and up 2. So 1 and 2. So I know my slope is rise over run. My slope is 2 over 1. And so my direction vector M is going to be the run, which is 1, comma, the rise, which is 2. All right, cool. And let's just graph that really quick, that vector. Remember, when I'm given a vector in the algebraic or Cartesian mode, it just means that we're starting at the origin and going straight to that point. And what do you notice about this vector? It's parallel to the line that we're trying to define. So that means that they are going to be collinear. We can move vectors around, that's fine. Now we need to deal with the position. And what do we know about the position? Do we know any dots that lie on this line? Yes, we know that the line we're trying to define goes through this point here, and this point is 1, 5. So in order to define our vector equation, we said we need a point on the line. We have that, and I need my direction vector, which I have. So let's find our vector equation. So our vector equation is, and here's what it's going to look like. So our vector is equal to the point on the line that we know, 1, 5. So the x and y value that we read off the graph, plus t, and t is our parameter, times our direction vector, which we defined by 2 points. So 1, 2, where t is an element of the real. Let's talk about that for a moment. Why do we say that t is an element of the real? That's because it doesn't matter. Like basically our direction vector just gives us a direction. It doesn't matter, or it applies to all values. So what if we like changed our direction vector? What if we had it expressed in a different way? What if I said that my direction vector was equal to, well, originally we said 1, 2. What if I said that it was equal to 2, 4? Would that matter? No, it would just look a little different. So if I sketch that vector here, starting at the origin, we're going to go to 2, 4. It's still pointing in the same direction. So that's totally fine. So if we multiplied our original direction vector, the one we just found, by 2, we're still pointing in the same direction. We still have the same slope. That's totally fine. What if we tried to multiply it by -1? So what if I said my direction vector was -1 and -2? Well, let's take a look. -1, -2 down here. The slope is still the same. We have to be careful with that because we're going in the opposite direction, but we're just defining a line. We don't really care about the direction anymore right now, so that's fine. So any value of t, so here t has a value of 2 times our direction vector, that's fine. We're still indicating the same direction. Our line's still following the same path here. We said t is -1. If we're just talking about a regular vector, that flips the direction, but that's fine because our line extends to both directions, in both directions to infinity. So that's okay. Let's take a look at a quick example here with our vector equation. What happens if our parameter is equal to 1? So if t is equal to 1, then our x components are going to be 1 plus my parameter, 1 times 1. So x is going to have a value of 2. My y components are going to be 5 plus my parameter of 1 times my y value, which is 2 for my direction vector. So I'm going to get 5 plus 2 is 7. And so this represents the point on my graph 2, 7. Is that allowable? Is that fine? Yeah, let's sketch that on a graph. So I'm going to go over 2 and up 7. And look, that's right in line with our line. So basically, the vector equation form lets us indicate any position, any spot, any location on our graph, or sorry, on our line using two pieces of knowledge. One, we need to know a point on our line where we can start measuring, so we know a point. And the direction vector just tells me you're going to move in this direction some multiple number of times. That's what the t tells us. So the t says how many times do I move according to the direction vector. And that can be, if t is positive, we're going to keep going up that way. If t is negative, we're going to keep moving that way. And t can be any value. So if I need to move a great number of ways, I can have a large value of t and I just keep going and going. Or if I needed to move a very small amount, t could be some kind of fraction or a negative fraction where I just move a little bit, or a small positive fraction where I just move a little bit. That's fine. So vector equation gives the equation of our line by giving us a starting point and a direction vector, and then we multiply by t to tell us how far in that direction do we need to go. Let's take a look at our next page and add a few other things to consider here. Find a vector equation of the following line. A few things to keep in mind. We're going to use vectors. We're going to start with our point. Which is at 4, 3. So we're going to start with our given point right here. Then we're going to add any multiple. So this is where we use a parameter. So we're going to multiply. So multiple of the direction vector. So we're going to need to define that at some point. And we can find any point on the line by substituting values of t. Remember, t is my parameter. So in my example here, my direction vector is given, my point is given. So let's plug those into our vector form of our equation. Vector r is going to be defined as 4, 3. Now let me just line this up a little bit better here. Just because I'm filling in a pre-designed note. So r equals my point. And notice here, just for a moment, we might think of this as simply a point, but we're actually using a vector here. So I'm going to have my point plus my parameter, t, times my direction vector, which is already given, -7, 1, where t is an element of the real. So t belongs to the set of all real numbers, so we can have any real value for t that's allowed. Question: how can this resultant vector define every single point on our line? Well, let's get a little more theoretical. We have the general formula here. My vector r is defined by p, which is a point on the line, so written as a vector, and m is the direction vector of the line. We've already mentioned this about P, but we're going to say it again, that we can think of it as a single point. So we often think of as a single point, but really it is a vector. And remember, when we define our vector as like a single point, we have the tail at the origin, 0, 0, and tip at the point P. So we're just discussing our P here. Remember, T is my parameter. So that's how many times we're going to multiply my direction vector. And we can think of this like a machine. This will land you on every point of the line, every possible point, as you let t equal different values. And I believe I kind of went over this on a previous slide, but we'll go through it again. And let's take a look at what's happening here. So really what we're doing here is just an example of vector addition. So let's take a look at our line right here. R is given as R0 plus t, so the parameter, and that's just like a scalar. We're just multiplying a scalar, some number, some quantity, times our direction vector m. So let's take a look. I'm going to add my vectors here. So I'm going to have my original vector, R0. So I'm going to go from the origin to the given point. And just like we said before, we can think of it as a single point, or we can think about it as a vector going there. And then I'm going to add my next vector, which is t times the direction vector. So direction vector is here. So if t was 1, it'd look something like this. T2 was something like this. And we can go along the length of our line, whatever multiples of m that we want to. We can have our t value equal to anything we want, and that's just going to move us up and down the line. So let's think of this one piece at a time again. So I'm going to have my direction vector, or like my point right here. So I'm going this vector. I'm going to add the next vector, which is some multiple of my direction vector here. So I put it tail to tip, and I can reach that point on the line. And as I change the value of t, my vector is going to maintain its direction, but it's going to have a longer and longer reach. Or if I multiply by a negative number, I can go back the other way. And because t is an element of the real, it can have any real value, I can slide along that line as far as I need to. Or in other words, the second vector, the vector I'm adding to here, will maintain its direction but will change length. So let's show that one more time. Add my original vector and my new vector, and my resultant starts at the start and ends at the end right here. And if I change my t value, so let's see that again, R0, I get to some point on the line, that's fine. I change my t vector and I have a longer value there for this component right here, that's fine. When I draw my resultant vector that starts at the start and ends at the end, I'm always going to end up at some point on the line. So as I change the value of t, always starting at the start and ending at the end, doesn't matter. My vector always points to some location along the line that we were defining here. Let's just tidy that up. There, that looks pretty good. So that's great. Let's take a look at some examples and actually try applying this. Example 1, determine a vector equation for the line y equals -3x plus 5. We're working in 2 space here, R2, so two-dimensional plane like we're familiar with. And we know our vector equation needs 2 components. It needs a point, and it needs a direction vector. Let's find those using our equation that we're given here. So first, what do I know? I know that my slope is -3. So m equals -3 or -3/1. So we can define our direction vector. We have our run, which is 1, our x component. And we have our rise, which is -3, our y component. All right, cool. I already have my direction vector. Do I know any points that lie on this line? Yes, I know that the y-intercept is -5. Remember, y-intercept occurs when x is equal to 0. So if x is 0, y is -5. And so the point 0, -5 lies on the line. So let's plug that in. Remember, vector equation looks like this. R is equal to P. So my point, or my position vector, plus T parameter times M, my direction vector. Let's plug in our values. So R is equal to the point that we know is 0, -5, plus T, and remember T is a variable. We don't need to define it as having any particular value right now. It can have any real value. And my direction vector is 1, -3. And remember that T is an element of the real, so there's no restrictions on the value of T as long as it's a real number. And let's take a look at what that looks like. Let's sketch our graph, our Cartesian plane. So I'm going to have my x and y coordinates, and I'm going to have my direction vector. Direction vector looks like that. It goes from the origin to 1, -3. And I know my y-intercept, 0, -5. So when x is 0, y is equal to -5. So that's going to be down here, -5. Let's switch up our color so it's a little more distinct. And we know it has going in the same direction. It's parallel to my direction vector. So I can kind of resketch. Actually, what I might be able to do, let's get a little fancy here for a moment. Let's copy our direction vector. And move that right down there, and we'll just erase the extra stuff. All right, that looks pretty good to me. And then now we know as we change the value of t, if we increase the positive value, it's going to increase in this direction. Or if we make it a negative value, it's going to go back in this direction. So we've defined, using our vector equation, this line right here. Also remember that there are more than one way to write this. We can change our direction vector as long as it's anything that goes in the same direction. So I could extend it. I could have maybe said, defined it as the point 2 and -6. And this would have been the same. So I could have also written this like this. The position vector stays the same. Well, I can give any point that lies on the line, but this is the one I was given, or could easily find from the question, plus t. And my values here could be 2 and -6. And that would be fine. If I find the ratio of these numbers, -6/2 is -3, still getting the same slope. So really, I can use any pair of numbers here whose quotient is equal to -3. That's totally fine. So I could also do this. R is 0, -5, plus t, 100, -300. But then that would be a little awkward, because every time I just wanted to move a little bit, my t would have to be some pretty small fraction, because if my direction vector is like way down here, this is going to be like 1/100, 100 times -300. Like, that's going to get a little annoying and awkward. So maybe don't do that. We'll try to keep it in the simplest possible mode. Just know that it is possible to have other values there. All right, cool. Let's take a look at example 2. Just tidy this up a little bit so we're not taking up too much space here. I think I erased a little bit too much there. That looks about right. All right, let's take a look at example 2. Because notice it doesn't say in these questions, determine a vector equation. Sorry, it doesn't say determine the vector equation. It says determine a vector equation. So we're finding, there's more than one possible way of doing these things. Example 2, determine a vector equation for the line containing the points E at -1, 5, and F, which is located at 6, 11. And question B, what is the direction vector that is perpendicular to this line? Let's start by choosing one of our points to use as the point for our vector equation. So we're working on A. And for my point, I'm just going to use point E. So my point is going to be -1, 5. Next, I'm going to find my direction vector, or a direction vector. There are appropriate equivalent ones. So M is equal to, and that's going to be the vector running from point E to point F. And so to find that, I'm just going to do the x, subtract the x coordinate. So x2, or x of F minus x of E. So 6 minus -1. And my y coordinate is going to be 11 minus 5. And we're going to end up with a value of 6 minus -1 is 6 plus 1 is 7. And 11 minus 5 is 6. So this is the direction vector, or a direction vector, that we can use for our vector equation here. So let's plug in our values. Therefore, equation is our vector r is equal to position -1, 5 plus t times our direction vector, which is 7, 6. And don't forget that t is an element of the real. And we'll just highlight this appropriately so we know that it is the answer to our question here. So it's good to make our conclusions and concluding statements easily identifiable, especially when we have messy writing and end up with stuff all over the page. Highlighting or being clear where your conclusion is makes life a lot easier for anyone trying to follow or mark your work. All right, next up, B. All right, for B, we're going to have to define a direction vector that is perpendicular to our original direction vector. So we need, we'll call this vector M2, perpendicular to our vector M that we originally found. And remember, how do I know when a vector is perpendicular to another vector? When the dot product is equal to 0. So we're going to need a vector M2 such that M2 dot M is equal to 0. So let's set our vector M2 equal to A, comma B. And I need something so that A, comma B times 7, 6 is equal to 0. And let's think of this in terms of our slope. So our original slope here that we're dealing with is 6 over 7. And what do we know about the slopes of lines that are perpendicular to each other? They are negative reciprocals. So if my original slope is 6 over 7, and my perpendicular slope is going to be a negative reciprocal, so original slope was positive, this is going to be negative. Instead of 6 over 7, it's 7 over 6. What does that tell us? It gives us possible values for our A and B here. So A can be -6, and B can be 7. And I'm just taking these numbers and plugging them in here. So let's try this. A is -6 dot 7, 6. So I'm going to have -6 times 7 plus 7 times 6. So -42 plus 42, which of course equals 0. So there we go. The question said, what is a direction vector that is perpendicular to this line? That would be our good old result here, M2 of -6, 7. And there are more than one value possible here. We could have used 7 and -6, but this is fine. In our next section, we're going to move on from the vector equation and take a look at the parametric equations of lines in R2 or 2 space.